So for this video, we're going to talk about the understanding of our nature of infinities in the field of mathematics. Infinity is one of the most fascinating and complex concepts in mathematics. While it often evokes ideas of boundlessness and the immeasurable, the study of infinity actually reveals a very rich landscape of varying sizes and types of infinities that differ significantly in their properties and their implications. This video will explore the different types of infinities in mathematics, focusing on the transcendental numbers, number sets, real number infinities, imaginary number infinities, and even complex number infinities. So let's talk about the concept of infinity. Infinity, which is denoted by the symbol of the looping 8, is not a number but an idea that represents an unbounded quantity. It arises in different mathematical contexts, but from the size of the sets to the behavior of functions and sequences, George Cantor, a pioneering mathematician in set theory, was very instrumental in formalizing the mathematical understanding of infinity as a whole. So we need to look at countable infinities versus uncountable infinities. Cantor introduced the notion that some infinities are larger than others through his work on set theory. He categorized infinite sets into countable and uncountable infinities. Let's talk about the countable infinities. A set is countably infinite if its elements can be placed in a one-to-one correspondence with the natural numbers. For example, we have a set of natural numbers like n equals the brackets for a set 1 comma 2 comma 3 comma dot dot dot, which goes on from the smallest numbers all the way up to infinity. This serves as a baseline for countability. Examples would include natural numbers, integers, rational numbers, and so forth. But despite rational numbers being dense, they are still countable because they can still be listed in a sequence. Now we can talk about the uncountable infinities. These are sets that cannot be placed in a one-to-one correspondence because they are uncountably infinite. The set of real numbers, for example, is a really good example of this. Cantor's diagonal argument that he made at the time, which is, we're talking about like, 2 centuries ago, this demonstrates that real numbers between 0 and 1 could actually form an uncountable set, revealing a larger infinity than that of the natural numbers. Think about what we're saying there. We're saying that you could have decimals and fractions that are so minutely small that they become an infinite number of numbers, even though you're only counting between 0 and 1. Crazy how that works, right? Imagine you could have like, countless numbers of zeros, then going all the way to 0.0000001, something like that, right? And so you can also go from numbers that you can actually achieve to numbers you can't even achieve at all, like the transcendental numbers, which, when you're actually working with decimals, those could be countable. But when you're working with transcendental numbers, like pi, which is a series of decimal digits that never repeat and never terminate, these are these transcendental sets that have an infinite number of numbers, but they're not even countable. So let's talk about the real number infinities. The real numbers encompass both rational and irrational numbers, and their infinite nature can be examined through. Cardinality is one of the biggest issues of what we like to look at in mathematics because this is the countability of numbers. So the cardinality, it could still correspond to a continuum. It's strictly greater than a particular set of numbers, but you still have these intervals that you have to worry about. And so no matter how uncountably infinite, you can still have whatever you want for your intervals. Now, your density is what exists between two numbers. And so, going back to that 0 to 1 example, your density could be, again, an infinity in and of itself. So, let's talk about imaginary number infinities. Imaginary numbers are multiples of the imaginary unit I, which you're looking at like something like the square root of -1 or something to that effect, which, we don't have a mathematical operation that can even accomplish that. So that's why it becomes an imaginary number, because there's really no way for us to actually solve that problem, at least not using the mathematics that we're used to using day in and day out. But nonetheless, we can still create these numbers, which are completely conceptually imaginary, and yet we can represent them, and the cardinality would go on, infinitely speaking. And so this would lead us to eventually what we would know as complex number infinities. So if we think about that, again, cardinality is an issue because we have a ranking, but the set itself is still uncountably infinite, and it would have the same cardinality as a set of real numbers. What about topology? Well, the complex plane encompasses both the real and the imaginary axes, which then contributes to a very, very rich structure. You can have infinities in different kind of functions as well. Very complex functions, including those that involve analytic continuation and residue theory, which encounter infinities in very unique ways, like poles and essential singularities. You also have hierarchies and the sizes of infinity. Cantor's continuum hypothesis deals with the possible sizes of infinite sets. It posits that if you could imagine a cardinality between a set of two numbers, this still remains undecidably infinite when you're looking at it in set theory. You also have Aleph numbers, and these sequence describe increasing sizes of infinity, which is why we began with the statement that infinity itself can be different from another infinity. You can have some very large infinities, you can have some very small infinities. It's quite fascinating to imagine that you could have infinities that are relatively smaller or larger than another infinity. But really, again, it depends on what kind of set you're working with, because at some point, even within a set that says like the set of real numbers, you're going to reach infinity at some point. Now, in terms of physical interpretations, infinity is a mathematical abstraction, and it finds relevance in physics, such as in the cosmology or when you're dealing with singularities and black holes. In conclusion, infinity, through seemingly a singular concept, can manifest in so many diverse and intricate forms across different mathematical domains, from the countable infinities of natural numbers to the uncountable vastness of real and complex numbers. The understanding of infinity challenges and expands our mathematical perspectives. Exploring these various infinities not only enhances our comprehension of the way numbers work altogether, but they also illuminate the profound depth of beauty inherent in mathematical theory. This exploration underscores the reality that while some infinities are indeed bigger than others, each serves as a testament to the boundless nature of mathematical thought. As Neil deGrasse Tyson once said, the universe doesn't owe you any explanation, and just because it blows your mind and you might find it mind boggling to understand certain concepts, it doesn't have to conform to a thing.